phase transitions involving the quantum Hall effect. So based on that title, you can see I have a confession to make. I was actually invited to the wrong conference. I was invited to Eduardo's 30th birthday conference. It took me a while to get here. So yeah, so it's an old problem. But I can say, nonetheless, it has strong correlations, disorder, topology, and definitely lots of frustration. So anyway, thank you for the organizers to invite me, and it's a pleasure to be here to celebrate Eduardo's legacy, and I consider him a very good friend, someone who I always enjoy running into in conferences. Okay, so here's the problem. So we have some experiments. So let's first talk about the quantum Hall effect, just to establish some notation. This is a simple thing. You have a 2D electron gas in a magnetic field. You drive a current, and you measure the voltage along and perpendicular. And in 2 dimensions, the resistance and resistivity have the same units, right, because we're in 2 dimensions. So the resistivity can be universal. And in the quantum Hall effect, the resistivity tensor is set by the quantum of resistance, h/e², times a matrix. So this is the longitudinal, it's 0. And the fractional part, the Hall is quantized. And so I'm going to use units. This is large. Everyone knows this. I'm just saying this for the units. So in units of h bar and c and e equals 1, h/e² is 2 pi. And you have the integer quantum Hall effect, where nu is the filling fraction, is an integer. And we will also consider a class of fractional quantum Hall states, where nu is 1/2k minus 1, where k is 1, 2 positive integers. Okay, so these are a subset of fractional quantum Hall transitions. This is largely a solved problem, understanding the phases. Everything is, what's not solved are the phase transitions. Let's call it quantum Hall transitions. And it's very simple. The phenomena is easily stated. At t equals 0, you have a magnetic field, and you tune the magnetic field, and you have a quantum Hall state, and you have an insulator. Or you can tune the magnetic field, and you have a quantum Hall state 1 with one value of this nu, and another quantum Hall state 2. And there's a critical point, which is the quantum Hall transition, which I'll focus on today. It's a continuous phase transition. There's disorder, and there's interactions. And it exhibits standard one-parameter scaling theory. So if you measure, for instance, the resistivity as a function of temperature and magnetic field, it's basically the data can be collapsed into a scaling function, FAB, which is some scaling function so if I define delta is B minus B critical, that's the tuning parameter. So this is just a scaling function of delta times t to the 1/nu(z). So this is standard one-parameter scaling theory. You can also measure nonlinear current voltage characteristics. And what you do is extract a characteristic electric field. And the electric field exhibits, so from the conductivity scaling, you get the product of nu(z). But you can also measure the electric field from nonlinear IV characteristics. And this exhibits scaling of the form nu times 1 plus z. So now you can essentially extract nu and z independently. And we know from experiments involving integer transitions and fractional transitions from back in the 90s and even ongoing to this day that nu is approximately 7/3 and z is equal to 1. Okay, very good. The point that I want to stress is that if as theorists, the first thing we do is free electrons. That's basically first and almost the last thing we do, right? That's all we know how to do. But this is insufficient. Okay? And why is that? There's a very simple reason why you have to think about interactions. If you solve the problem of free electrons in a Landau level with disorder, I plot the density of states as a function of energy. Here's one Landau level. It's broadened by disorder. So what you have is, in the presence of disorder, these states are localized, these states are localized. There's one energy at which you have a delocalized state. Delocalized. And so if you ask, what's the conductivity at any finite temperature? After all, our experimental friends only measure at finite temperature. So if you have the conductivity tensor at t greater than 0, let's say the DC longitudinal conductivity, you weight a bunch of states within, say the chemical potential lies even at the extended energy. You will weight a bunch of states within a width of k Boltzmann times the temperature. And the extended state, the delocalized state, occupies a set of measure 0. And so what you'll find is the striking conclusion that any finite temperature transport, DC transport, is 0. So the reason in experiments it's non-zero must be a deviation from free fermion physics. The other thing that makes this free fermion models insufficient is the dynamical scaling, which is set by this exponent z. So if you look at non-interacting electrons, yeah. If you don't, inelastic scattering require interactions with phonons or something like that. Yeah. Okay, so if you ask about dynamical scaling, it all comes from the finite density of states. So density of states is a number per unit energy per unit length to the d, right? So this says that energy scales like length to the minus d, or z equals d, which in our case will be 2. And experiment says it's 1. So motivated by this, some people a long time ago said, hey, if you have Coulomb interactions, U goes like 1 over R, then maybe Z could be 1, because you have, after all, some energy scale that goes like 1 over a length. I would say that's the status of the theory of what the dynamical scaling law should be. But today I hope I will present something more sophisticated. Okay. So interactions are important. So now if I plot the phase, let me stick with yellow. Which do you prefer, yellow or white? Does it matter? Yellow? Okay. So if I plot the phase diagram again at t equals 0, now this is a theorist's phase diagram. So we have a quantum Hall state, and we have an insulator. Now let me invoke Coulomb interactions. I put E tilde because it's not the E here. You know, that E is what you get into the Lorentz force. E tilde involves a dielectric constant. Okay? So if you plot the phase diagram as a function of E tilde is dimensionless. So if I have E tilde squared over 1 plus E tilde squared, this is 0 and this is 1. So 99% of theory lies here on this axis, non-interacting electrons. The real phenomena is somewhere over here that we wish to understand. And this transition without interactions that most people study is known as the Chalker-Coddington model or various forms, falls under the class of transitions known as Anderson transitions. So this is very reminiscent of what Vlad was saying. If you think of the Anderson transition of 3D metal insulator transitions, you just tune across a mobility edge. It's similar here. You just tune across this delocalized energy here. But they are all peculiar in the sense that there are no thermodynamic singularities. Non-interacting electrons with a finite density of states have no thermodynamic singularities. By contrast, a true quantum critical point has both dynamical and thermodynamic singularities, right? Because you can't disentangle dynamics from thermodynamics from a quantum phase transition. So the real thing we wish to understand is out here. It's a quantum critical point. In the mid-90s or late 90s, Deng-Hai Lee showed that if you ask what is the scaling dimension of Coulomb interactions, it's relevant. So the flows take you away from here. So then, if we start with electrons at weak coupling and perturb with interactions, we don't know what to say. We don't know what happens with interactions. Moreover, if you ask about fractional quantum Hall states where the filling fractions are like this, and they also have transitions, if you start with a non-interacting limit, there's no way to ask, are they in the same universality class as the integer effects or not? So that's another issue that we can't address from here. What we've been doing over the past few years is to think about this problem on this line, where the Coulomb interactions are infinite. Now that sounds a little bit mystical. I'll demystify that in a minute. But what you find, let me just give you the summary. You find here, there's a phase transition between a quantum Hall state and an insulator. But remarkably, even if you're at infinite Coulomb interactions, it also is this funny Anderson-type transition. So we have an Anderson transition here and an Anderson transition here. Turns out that they're actually the same universality class, even at zero coupling and infinite coupling. But the case I wish to make for you today is that even though this is the wrong theory of the experimental phenomena, it gives you a window into the real phenomena that's much better than the one down here. The mean field, okay, so from this standpoint, the standard method of solving has been, if you want interactions and disorder, you have to guess the answer. But from here, we'll have a more systematic mean field plus fluctuations like we teach our students in StatMech courses. Furthermore, we can ask about integer versus fractional transitions much more easily. And so in this talk, what I wish to show you is, this talk, some exact properties of this transition as viewed from infinite coupling. Okay, any questions so far? Yeah. Yeah. Yeah, that's right. Was that a question or, okay, that was it, yes, okay, good. All right. So hopefully, now I'm going to go into some slightly more technical discussion, but I wanted everyone to get across this picture before I move on, okay? Now what I'm going to, yeah, Claudio.
Is there an exact quality?
No. But it seems mysterious, okay? It's possible that the real quantum critical point is self-dual, but the top and bottom are not dual to each other. Okay, so that's the overall summary. How much time do I have? Okay, all right, halfway already, okay. So I'm going to write down some equations. And don't expect to understand everything that I say, because this is summary of several years of work into a 20-minute lecture or talk. So I want you to not take the equations too seriously, but what the conclusions are based on them seriously, okay? Because we don't have much time. So, we're interested in critical phenomena. Critical phenomena is kind of a forgiving enterprise. You don't have to get the microscopic details right. You can choose whatever model you want to get the universal physics. Right? So what I'm going to do is start with, think of Dirac electrons. Sort of like graphene, but a spinless version of graphene. And so the Lagrangian, A is an external applied lab electromagnetic vector potential. The electron theory is something like this. There's a Dirac electron coupled to this electron external field. I'll explain what each of these terms are. And now there'll be disorder, and there'll be interactions. This represents a massless Dirac fermion in 2 dimensions, coupled to an external field. There's no spin anymore. You might know from studying topological insulators or something that if you put Dirac electrons on a lattice, there's always going to be a partner heavy fermion. Right? There's always a doubler on the lattice. This might be at the surface of a topological insulator in 3D, but in bulk 2D, they come in pairs. And if the partner happens to be massive, you can integrate it out, and you get what's called a half Chern-Simons. So this here, ADA, is a shorthand for epsilon mu nu rho, a mu d nu a rho. Okay? So this is called the Chern-Simons term. It gives rise to Hall physics. So this represents a microscopic theory of Dirac electrons on a lattice. Now, we'll have disorder where we have a random potential coupled to the density of electrons. That's the standard way of disorder, where V of R is a quenched variable with zero average and some non-zero variance, say some Gaussian random noise. And then finally, the interactions will be E squared R prime n of R prime over R minus R prime. This has everything you wish. If you can solve this model, you would solve the problem. But the only method we know how to solve this is, God gives Bob Laughlin the answers and he tells us what the answers are. So there's not a very systematic way of solving this. But I'll tell you what you do when since you can't solve both, you can solve the problem in the non-interacting limit. That becomes free fermions. This should be E tilde. When you have no interactions, you get a phase diagram that looks like this. I'm not going to, in the interest of time, I'm not going to derive this. So there's a magnetic field, which is the curl of A. And there's the electron density. And you have a line here at B over 4 pi that separates two phases. One is the quantum Hall state. Actually, this is the integer quantum Hall state with sigma xy either 1 is equal to 1 in the units of the quantum of conductance. And then there's a trivial Anderson insulator. And there's a phase transition. And the phase transition can be approached by varying the magnetic field, which is what's done in experiments, or by varying the density at fixed magnetic field. If there's a one-parameter scaling theory, it shouldn't matter which you do, you get the same exponents. So for later convenience, I'm going to choose this approach, and you'll see in a minute why. This transition, we understand the phases quite trivially. This is like a mean field theory at non-interacting electrons. But you can't ask about integer versus fractional transitions. You can't ask what the critical conductivity is here. You can put it on a computer and solve it. You get answers. No problem. So the reason I choose this model is that there is a dual representation. So we can invoke duality to go from one theory to another. So the electron Lagrangian has a dual. You should think of this as, if this is the electron, the dual theory involves the vortices of the electron. It's very much like boson-vortex duality, which has been well established, but now there's a fermionic analog of that, which has also been well established in recent years. I'm not going to prove it for you here in the interest of time. I can say that lots of people have worked on it, myself included. You can put it on a lattice and do fairly rigorous things, and we've done some of that. So the dual theory, in terms of vortices, also depends on the background field. A, big A, is written like this. There's a dual fermi, the vortex, which I'll call C. It is coupled to not the electromagnetic field, but some dynamical field, little a. And it also has this massive partner, so this is the statement of the duality, but then we can add in the disorder, and we can add in the interactions. Okay, so you analyze this, and we can ask what is the electron density? The fact that it's a dual theory, which means that you can obtain the density by differentiating this theory with respect to capital A, or this theory with respect to capital A, and you get the same answers. So the electron density is dl, the time component of A, which I'll call A0. And this will be big B minus little b over 4 pi, where little b is curl of little a. And A is a dynamical U1 gauge field. So you path integrate over little a, but not over big A. That's the point. Yeah. 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 You can call them composite fermions, but they're like composite fermions. They have many of the same flavors. Yes? Flux attachment. You can do flux attachment heuristically, but that's been done forever. But my point is that with the Dirac Lagrangian, you can actually do it as a statistical mechanics duality. It's on a firmer ground, which is why I use this. That's a great question. OK. We also know we can have the equation of motion of one component, A0, that couples to the fermions. What you find from that is basically the expectation value of C dagger C, the vortex density, is equal to B over 4 pi. So this is why we call them vortices, because you see the number of these particles depends on the external magnetic field. Okay? So that's why they're vortices. Now, you see, so far, this is a strongly interacting theory, and so is this. So what have we gained? Nothing so far. But when we add disorder, since the disorder couples to the electrons in this theory, the electron density is up to a constant, just the random is a magnetic field. So the disorder Lagrangian is going to be minus V of R, B of R over 4 pi from this expression. So what that means is that while the original theory was coupled to a random scalar potential, the dual theory is coupled to a random vector potential. A has a random component, random, and then also a fluctuating piece, which depends on R and T. Okay, so this is a quenched piece and a dynamical piece. Because it has a random magnetic field, that implies a random vector potential. Now, the real utility comes from the interactions. So interactions is density, right? But since the electron density is related to the flux, the interactions will be E tilde squared, B of R prime, over R minus R prime. So you see that the charge enters the numerator, not the denominator. If you think about Maxwell theory, F mu nu squared over 4E squared, something like this. This is a weakly coupled theory at E goes to 0, right? But here, this is weakly coupled at E tilde goes to infinity, because the fluctuations of little a are severely suppressed when E squared goes to infinity. So that's the advantage. When E goes to infinity, there's mean field theory. And when E squared is finite, we have gauge fluctuations. Okay, so that's the reason, what I drew earlier, we had a theoretical approach. Oh, it's right here. We can work up here and solve this problem. Up at E squared equals infinity, it's just mean field theory. But I want to argue that it's a much better mean field theory. So I'm going to run out of time, so I'm just going to give you a flavor from what follows. Are there any questions so far? No questions. All right. I'll keep this. Yeah. Big A? This one. Non-local?
No, could it be like an analog of a vector potential, like the ones that we have from Berry connection, for example?
Well, so I'm thinking about experimental phenomena here, where you apply magnetic fields and think about charges, real electron charges. So it represents the physical electromagnetic field.
Okay, thank you.
Okay, oh, let me just say one other thing. You can work in a gauge where you have a time component and a transverse component. And this magnetic field is purely the transverse, involves the transverse fields. And you can Fourier transform. Remember, 1 over R in 2D is 1 over K. And there's 2 Ks in the numerator. So that will be like E tilde squared times K, A transverse, A transverse. Okay, so that'll be coming in handy later on. So when you have a infinite charge, when you have mean field theory, we can now write down a phase diagram. And the phase diagram involves the study of free Dirac fermions in a random vector potential. But there will be, since there's an external magnetic field, there will be a finite density of these particles. So I can tell you what the answer is. That's free fermions. That's a trivial problem. We know how to solve that. The answer is this. There's density of states as a function of energy. So let me put the chemical potential of the vortices here. This is energy, mu vortex. The problem of Dirac fermions in a random vector potential is well known. There are, so since B of R has a quenched random field, we can talk about its spatial average, which I'll call B0. And you can see from here, B0 depends on the average electron density, which I want to tune in this experiment. I don't want to tune the magnetic field. I'm going to tune the electron density. So this will be play the role of the tuning parameter. So I'm going to put my Fermi level here, because that's determined by the external magnetic field, capital B. And I'm just going to hold it fixed. And when B naught is non-zero, there's a 0th Landau level of the Dirac electrons, which the number of these modes is equal to the number of flux quanta of B0. And because these are Dirac electrons, you only half fill them. So when B naught is not equal to 0, sigma xy of the vortices is 1 over 8 pi times sine B0. Okay? So if you change the sign of the magnetic field, the Hall conductance will change sign. Make sense? Okay? But then we have to remember that we have a partner fermion. The doubler fermion will also generate a minus 1 over, sorry, this is a 1 over 4 pi. Not that it matters. It may not matter, but. So you can see that when B0 is positive, Hall conductance vanishes. That's the dual description of the insulating phase. And when B0 is negative, the Hall conductance of the vortices is minus 1. When you translate back, you get plus 1. So that's the quantum Hall phase. So that's how you see the phases. But the very interesting thing that happens here is what happens when B naught is equal to 0. So you have the problem of Dirac electrons at finite chemical potential with a massive partner, and they're both subject to a random vector potential, whose average is 0. So we know from this, the massless fermion has a statistical time reversal symmetry. It cannot generate a Hall conductance by symmetry. The entire Hall conductance comes from the partner fermion. So when B naught equals 0, sigma xy of the vortices is exactly this, minus 1 over 4 pi. It's a half, exactly 1/2. Okay? And that is extremely significant. Let me go over here. It's very significant because of Laughlin's gauge argument. So what I'm going to prove to you, oh, am I already done? 5 minutes, okay. So I'm still doing just the mean field. That's, so this is, the fact that the Hall conductance is half quantized implies that at B naught equal to 0, you put the Fermi level here, these are all delocalized states, whereas these are all localized states. So the states go from being all localized to all delocalized. The reason for that is because the Hall conductance is minus a half in units of E squared over H. So I'll say it in words. The Laughlin gauge argument says that if fermions if states at the Fermi level are localized, the Hall conductance must be an integer. So the contrapositive of that argument is if the Hall conductance is not an integer, the states at the Fermi level cannot be localized. Does that make sense? So what you have here is a dramatic effect where you go from having all states localized with a Landau level to all states delocalized without a Landau level. Okay? So it's an extremely interesting effect. But now, that's all just at the mean field theory. But now, since we have a finite width, a band of energies which are delocalized, there's no issue with DC transport. We can easily do it. Let me also say one other thing. If you want to study fractional states where you have 1 over 2n minus 1, where n is 1, 2, and so on, this theory has a trivial tweak. You just put an n right here, and you're done. So you can see that in mean field theory, the fermion part is doing the same thing. This part is changing, but that just changes the value of the resistance at the transition, but doesn't do anything to the exponents. So that's a trivial statement of this notion of super universality, that the integer and fractional transitions are in the same universality class. But this is kind of a dumb statement. You know, if you do mean field theory, you get mean field exponents. Landau theory of phase transitions is super universal. So I'm not saying anything that's substantive, but that's the understanding that has existed up to now. Next thing we want to do is go away from mean field theory, include fluctuations, and then show the conditions under which the transitions are in the same universality class. So I don't have much time, unfortunately. So what I'm going to do is tell you, I'll just say in passing, we can study this since at mean field theory, these are free fermions, you can put it on a computer, you get the same exponents as the Chalker-Coddington model. So remarkably, at infinite coupling, you get the same critical exponents as at zero coupling. So when E squared is finite, what happens? So there's one technical thing which I cannot go into because the chairman is standing right in front of me. So I'll just tell you, we made an exact analysis of this problem. One exact thing can be stated, is that sigma xy of the vortices is independent of E squared. So if you can compute it at E squared equals infinity, you know it at finite E squared. That's an exact statement that comes from anomaly matching, and I don't have time to go into it, unfortunately. But this means that even at finite E squared, at the critical point, due to the corollary of Laughlin's gauge argument, states at the Fermi level are not localized. So that means that sigma xx of the vortices, since the states are delocalized, is less than infinity and greater than 0. It's a rigorous bound of the conductivity, okay? So, but this will be all I need. I don't need to know the exact value of this. We don't know. We can compute it. In the future, we wish to compute it. But right now, this is all you need. The reason is this establishes the fact that z is equal to 1 at the critical point. How does that happen? If you have only gauge fluctuations determining the dynamical exponents, you can ask, what is the transverse gauge propagator? Because of Coulomb interactions, there's this piece, which goes like 1 over e tilde squared k. And then there will be a quantum correction, which comes from the exact current-current correlator. I don't know what the value of the current-current correlator is, but I know that this number is finite. So from Kubo, we know that Jj is I omega sigma. So this can be replaced by I omega sigma xx of the vortices. So this shows that z is 1. So the beautiful thing is that this requires interactions and disorder. Okay, without both, you can't establish this. The last thing I'll say is there's a back of the envelope. So the rest is just downhill skiing, okay? You have to accept this, I'm afraid. This is the key point of my talk, and I can't prove it to you. But the other thing that we can ask about is the nature of the notion of super universality, namely that integer and fractional transitions belong to the same universality class. Now, one thing that we find is since the conductivity is some number between 0 and infinity, and also the diffusion constant is finite, by Einstein's relation, the compressibility is also non-zero at the critical point. So if kappa is non-zero, kappa is the compressibility. We can establish the universality of integer and fractional transitions to be the same. And it goes like this. If you just look at the gauge part, the part that only involves the gauge fields, A0 and A transverse, call this gauge. There's a bunch of other stuff, which I don't need right now. The way it enters is there's a compressibility, A0 squared, okay? And the Coulomb interaction plus disorder gives me an E squared K minus I omega sigma A transverse. But now, all the data about integer versus fractional transition is encoded in a so-called Chern-Simons term, which I'll denote schematically by lambda, which is A0 of the form A0 K A transverse. And I can tell you what lambda is. Lambda is 1 over 8 pi n, 1 minus n. Okay, so n here enters the nu. So nu is 1 over 2n minus 1. But now you can see that since the system is compressible, this looks like a massive time component of the gauge field. So you can integrate it out. When you integrate it out, you will get a theory that involves the lambda, and so only the transverse, so L effective, is going to be A transverse E squared K minus I omega sigma. But then when you integrate out A0, just a trivial Gaussian integral, you get minus lambda squared over 2 times compressibility, K squared A transverse. So you see that the information about fractional versus integer quantum Hall transitions enters in a subleading effect in higher derivative terms. So it's formally irrelevant in the RG sense. So the information about integer versus fractional transitions is encoded in an irrelevant operator. So this is now a fluctuational statement. This is not a trivial Landau theory-like statement. So this proves that with Coulomb interactions, the integer and fractional transitions must belong to the same universality class. Now, I'll just say one last thing, and then I'll be done. In experiments, people are now starting to gate the quantum Hall system and screen the Coulomb interaction. Okay? When you screen the Coulomb interaction, what happens? Well, screened Coulomb. You put gates, top and bottom gates. In the theory, what happens is now there's no 1 over r anymore. There's just k becomes k squared. So you replace everything I said. Whenever you see a Coulomb interaction, you change it by k squared. So you go here, and that says z will be 2. So the dynamical scaling laws will change. But also, if you put a k squared here, now you see that the difference between integer and fractional transitions is no longer subleading. It's sort of at the same scaling dimension. So we have the interesting possibility that if we screen the gate with gates, the transitions may not be in the same universality class, whereas if we don't screen them, they will be. Okay? So that's the sort of insights that I wanted to convey in this talk. So let me just summarize. This is the summary of my talk. We have magnetic field. We have interactions. We have here a Chalker-Coddington model. Nu is 2.59. I actually didn't say this in my talk. And then we have at infinite Coulomb interactions work that we did, where also z is 2 and nu is 2.59. Remarkably, the exponents are the same. Interactions are relevant in both directions, but from the infinite coupling limit, you have a better angle of vision into this. We can have some exact properties, as I've showed you here. Z is going to be 1 for Coulomb interactions, and nu, we don't know yet. Okay, thanks.
Thanks, Sri. I have time for a couple of quick questions.
I have a question that might be a bit naive, but I'm going to ask anyway. So what you told us in the case that E tilde is infinity and B0 is different than 0, remembered me a lot from what happens in an axion insulator, that we have a bulking gap.
In an axion insulator?
Yeah, that we have a bulk, a gap in the bulk. And then we have a surface state that comes with half of the axion angle. And so it's half quantized, anomalous Hall in the surface.
Yes.
If the surface is insulator, because if it is metallic, then the Dirac cones contributes with other half, and this effect cancel out.
Yes.
So I was wondering, is this field theory the same theory that describes an axion insulator if I go to 3D?
That's a very good question. I think if you have the Coulomb interactions may be different, though, because it still remembers that it's coming from 3D. Right? So then 1 over r becomes 1 over q squared, you know?
I see.
So that might be one difference. But if you have just a, you know, that's the only conceivable difference.
And I think the Simons, the Chern form that you started, that you use A del A, you would also have another term, right? Because in the Chern-Simons form, but this I might be wrong, because they're in the Chern-Simons form for the axion insulator. You have, it's in terms of the Berry curvature, and we have A del A, and then you have a term that is multiplications of A. That I don't remember by heart.
You mean like A cubed or something?
Yeah.
Oh, so that's a non-abelian Chern-Simons
Yeah,
term.
it's the tree form.
Here it's all abelian, so
Okay.
that term doesn't arise.
Okay.
So it's just U1.
Mm.
Yeah, I think that's right.
Okay, thanks.
Yeah.
So thank you for this nice talk. My question is related to that limit of high energy of the charge goes to infinity. You mentioned that the conductivity x sigma xx doesn't depend of the charge
Sigma
in the
xy.
finite xy, right?
XY, yeah,
Correct.
XY.
Yeah, sorry, sorry. So
Yeah.
you mentioned that might be related to the fact that in the high energy limit we have an anomaly. And I was wondering if this is the Hofft anomaly that people are working right now. That it means that that anomaly might be there even in the infrared limit when the charge goes to 0. So if is that correct, it might be a little. Just finish.
Yeah. Oh, sorry. Please go ahead.
If that's correct, I might be a little bit confused in the fact that you also mentioned in the beginning of your talk that you also have a phase diagram and you put the density and the vertical axis and the magnetic field in the horizontal one, right?
Yeah.
So you can think of the phase transition along that density direction. So in my mind, it might be strange that if you decrease the density, the conductivity doesn't change at all. So
the Hall conductance doesn't depend on the density.
Yeah, you're right. You're right.
Yeah.
But
so it only depends on, I changed the density and the field such that the filling fraction is not changed, right? So then the Hall conductance need not change. Because I'm also changing the magnet. If I just march along the axis, for a fixed magnetic field, there will always be a quantum Hall state and an insulating state. The quantum Hall conductance doesn't depend on the density. So, yeah. So I was going to say something different, which was a more technical thing, but I'll save that for private conversation about the anomaly thing.
Okay, so in the interest of time, I have to move on. Let's thank Sri once again for this
Thank
nice
you.
talk.